Welcome to these NPTEL lectures on dynamics and control of mechanical systems. In this week, we have been looking at design of controllers. My name is Ashitava Ghoshal. I am a professor at the Department of Mechanical Engineering, Center for Product Design and Manufacturing, and also in the Robert Bosch Center for Cyber Physical Systems at the Indian Institute of Science, Bangalore. In the last two lectures, we had looked at the design of a PID controller, how to find the gains, P, I, and D gains. In the second lecture this week, we had looked at how to design a controller using root locus. In this lecture, we'll look at design of controllers using state space design. In this lecture, we'll look at the design of controllers for mechanical systems using the state space formulation. Before we start on the topic of design, let us quickly recap what we know about state space and what exactly is the state space formulation. The state space formulation is basically the equations of motion linearized, and then we have ordinary differential equations in time domain. We also have algebraic equations which relate the output to the states. So the state equations are given by x dot equals fx plus gu. X are the state variables, they could be n of them. U are the inputs to this plant and they could be m of them. And we also have an output equation which is y is equal to hx plus ju. Okay, so h is a constant matrix, j is also a constant matrix, f and g are also constant matrices obtained from linearization of the equations of motion about an operating point. So as I said, the state variables x have dimension n cross 1. The control inputs to the plant have dimension m cross 1 and the output variables have dimension p cross 1. In a block diagram form, what we have is this dynamical system which is given by x dot equals fx plus gu. The input is u and u could be from a controller, and one of the simplest controller is when u is given by u equals minus k into x, where k is the constant matrix. So the input to the controller is typically the error, which is r of t minus y of t. However, in the state space formulation, for the moment, we will assume that this r of t is 0. We also do not have the direct term j into u. So you can see y is just h into x. There was a y equals j into x plus j into u. So we are not going to consider the direct term. And as I said, there is no reference input to start with. Later on, we will introduce the reference input in the state space design. The simplest possible controller could be u equals minus kx. So x's are the state variables. So k is a matrix of k1, k2 all the way till kn. We also remember that these are linear systems. These are single input, single output systems. So the reference trajectory when we introduce will be one dimension. The output variable y is also one dimension and u is also of 1 cross 1. So hence this k is a 1 cross n matrix into x, which is n cross 1. So u will be a single input to the dynamical system. So if you substitute u equals minus kx in the equation of the dynamical system, which is x dot equals fx plus gu, we will get x dot is equal to f minus gk into x. The characteristic polynomial for the closed loop system is determinant of Si minus f minus gk. Okay, so this is a nth degree polynomial in S containing k1, k2 all the way till kn. Let us take an example to see each of these terms more clearly. So we have this inverted pendulum. So this is a pendulum which is opposite to this gravity vector. It is making an angle theta from the vertical. We can derive the equations of motion. We have derived it earlier. And then we can linearize about theta equals 0. So then what you will get is x1 dot is equal to x2, and x2 dot is omega square into x1 plus u of t. So we've assumed that there is an input which is like a torque, and this omega 0 is square root of g by L. So these equations were derived earlier using the Lagrangian formulation, where we found the kinetic energy, the potential energy, and then we did some differentiation, and then we could derive the nonlinear equations of this inverted pendulum. So if you write it in this form, linearized about theta equals 0, where theta is measured from the vertical, we will get these state equations. In these equations, there is no damping. And you can see that the characteristic polynomial of this f term, so this is f into x plus g into u. So the eigenvalues of this f matrix are plus minus omega 0. And recall, I have shown you that the eigenvalues of f are also the open loop poles. So in this case, the poles are at plus minus omega 0. So one pole is in the right half plane, and hence it is like an unstable system. So if you give some input, the output will continuously increase with time. So let us say now that we want to design a controller such that the desired closed loop poles are at s equals minus 2 omega naught. So basically in the s plane, we had plus omega naught, minus omega naught, and the controller poles should be at minus 2 omega naught. So there are two of them. So continuing, so the desired closed loop characteristic polynomial is s plus 2 omega naught whole square, and we can expand this as s square plus 4 omega naught s plus 4 omega naught square equal to 0. The determinant of the closed loop system, or the characteristic polynomial of the closed loop system, is determinant si minus f minus gk. And remember, what is f? F is 0, 1, omega 0 square 0, and k is k1, k2, and g is 0, 1. So when you substitute all that and we compute the determinant, you will get s square plus k2s plus k1 minus omega naught square equal to 0. So if you compare these two equations, this is the desired closed loop characteristic equation, and this is the characteristic equation with k1 and k2. So what you can see is k2 is 4 omega naught. So k2 is 4 omega naught, and k1 is 5 omega naught square. So we have a system of equations now where x dot is equal to fx plus gu, and u equals minus kx. So we can substitute all these things and solve the equations using MATLAB. So we have to do it numerically. We can also probably do it symbolically because it's a very simple equation, but let's do it using MATLAB. So if you give some initial condition x of 0 as 0.1 and 0, so 0.1 means the pendulum is slightly perturbed from the vertical. So this, remember, x1 is theta and x2 is theta dot. They are the state variables. So if you just give a small perturbation, the normal natural dynamics of the system is that theta will increase. That is obvious. So this is a pendulum which is inverted, and if you just perturb it a little bit from the vertical, the angle theta, which is measured from the vertical, will keep on increasing. And this blue curve shows that perturbed theta. Okay, it increases with time. However, when we use u equals minus kx, okay, where k1 is 5 omega naught square, k2 is 4 omega naught, and in these examples we have chosen omega naught equal to 1. So then you can see that the plot of theta goes back to 0. Okay, so we have a unstable system, So small perturbations will increase with time, but when we use u equals minus kx, we use a controller which is designed such that the closed loop poles are at minus 2 omega naught. Okay, so on the left half plane. So then the output theta goes to 0. We can also see what is d theta by dt. So the d theta by dt will increase, whereas after we use the controller, it will decrease for a while and then it goes back to 0. So theta dot goes to 0 means the pendulum is no longer moving, and theta goes to also 0. So continuing with state space design, let us consider a little bit more complex system, a third order system, which is given by this third derivatives of y plus a1 into second derivative of y with time, a2 dy by dt plus a3y, and the right hand side now has both u dot and u double dot. So it is b1 into u double dot is d2u by dt square, b2 into u dot plus b3 into u. We can obtain the transfer function after taking the Laplace transform of this ordinary differential equation. So ys by us will be given by b1 s square plus b2s plus b3 divided by s cube plus a1 s square plus a2s plus a3. This can be represented in this block diagram. So we have an input u, then this is integrated, once more integrated, once more integrated, and then we at this place you have u, so b3 into u, then b3 into u dot and b1 into u double dot, whereas if you go back from this side, you will see that you will have a1 into some d2y by dt square, then a2 into dy by dt, and a3 into y. That will be given by, so this block diagram represents basically the same transfer function. In the state space representation, we can also write x1 dot is minus a1 x1 minus a2 x2 minus a3 x3 plus u, and x2 dot is x1 and x3 dot is x2. Okay, so this is another way of writing this differential equation. So the corresponding F, G, and H matrices can be written in this form. So there is a subscript C, and we will see why I am using the subscript C in a short while. So this FC is minus A1, minus A2, minus A3, the first row. The second row is 1, 0, 0. Third row is 0, 1, 0. And the G matrix is 1, 0, 0. And the H matrix is B1, B2, B3. So now if you want to find the characteristic polynomial of the closed loop system with U is minus G into K, so that is determinant of F minus GC into K equal to 0, we will get this cubic polynomial, which is S cube. The coefficient of S square is A1 plus K1, S is A2 plus K2, and this is A3 plus K3. So K is K1, K2, K3, a row vector. So if the desired polynomial is, let's say, another cubic, which is S cube plus alpha 1 S square plus alpha 2S plus alpha 3 equal to 0, then we can just compare these two cubic equations and we can clearly see, very easily see, that K1 is alpha 1 minus A1. K2, A2 plus K2 will be alpha 2, which is K2 is alpha 2 minus A2, and K3 is alpha 3 minus A3. So hence, if the matrix F and the matrix G and the matrix H can be written in this form, these are very easily used to obtain K1, K2, K3. So a matrix F written in this form, which is first row is minus A1, minus A2, A3, and so on, these are called as the upper companion form or also the controller canonical form. So this C basically means that F is in the controller canonical form. GC means it is in the controller canonical form. So whenever you have a controller canonical form, this G is 1, 0, 0. Okay, and F is in this form, minus A1, minus A2, minus A3. Second row is 1, 0, 0 and 0, 1, 0. So I have purposely taken this simple cubic example because very easily we can see what is the controller canonical form or the controller G form. Okay, the G in the controller canonical form. If you have n dimensional, if you have a nth degree ordinary differential equation, so you can see this will become minus A1, minus A2 all the way till minus AN, and similarly this is 1, 0, 0 all the way, and then you can keep on shifting. Okay. So the algorithm to obtain controller gains when it is n dimensional is first form the FC and GC matrix. Okay, so find F and G in the controller canonical form, then obtain determinant of FC minus GCK, which will be at nth degree polynomial of the form Sn, and then A1 plus K1 s to the power n minus 1, and so on An plus Kn. And then if you are given a desired closed loop polynomial of the form s to the power n plus alpha 1 s to the power n minus 1 dot dot alpha n, then we can just by inspection obtain Ki as from this expression, which is Ai plus Ki is equal to alpha I for I equals 1 through n. So in summary, if the state space realization is in upper canonical form or in the controller canonical form, the controller gains can be obtained by inspection. So the natural question is under what conditions we can convert a normal F and a G to the controller canonical form FC and GC. And it turns out that this can be done only if the system given by FG is controllable. Remember, we had discussed something called controllability. We had discussed a matrix called Kalman matrix QC, where the first column was G, second column was F into G, and so on. So if the rank of that matrix is n, we said that the system given by x dot equals fx plus gu is controllable. And it turns out, and this is very interesting and not very obvious why it should be, that I can convert an state space realization which is x dot equals fx plus gu into x dot equal fcx plus gcu, meaning in the controller canonical form, only if this f and g is controllable. So let's continue a little bit. The general state space formulation with one input can be written as x dot equals fx plus gu. Now x is a n by 1 vector. We can obtain gain k such that u equals minus kx gives a desired polynomial which is determinant of si minus f minus gk equal to 0. Now let us consider the transformation x is equal to p into z. Okay, so we are doing a linear transformation. So from the state variables x, we want to go to state variable z by means of x equals pz, and this matrix P must be of rank n. So there is no problem of converting from x to z or z to x. So P inverse must exist. So in terms of z, the state equations can be written. So we can write x dot is P into z dot. So we can write P into z dot is equal to f into P into z and so on. And then we can pre-multiply by P inverse. So we can write z dot is equal to P inverse f pz plus P inverse z. Okay, we have seen this earlier. So when we first discussed state space, we discussed how we can use the matrix P to diagonalize this F matrix. Okay, here we are not going to do diagonalization, but basically we are doing some transformation from x to z. So let us call this P inverse Fp as some f bar z plus g bar u. The controllability matrix for f and g which is qx. It is g, fg, f to the power n minus 1g, all these column vectors. The controllability matrix for f bar and g bar can be similarly written as g bar, f bar, g bar, and then f bar to the power n minus 1 into g bar. And we can rewrite g bar. So what is g bar? It is P inverse g. Okay, so g bar is P inverse g, f bar is P inverse fp, and so on. So hence we can rewrite all these terms f bar and g bar in terms of original g and f, and it turns out that you will get terms like P inverse fp, P inverse g. So P into P inverse is identity. So we will left with P inverse f into g. Okay, so we can take out P inverse outside because every term will have a P inverse. So we'll have P inverse g, then P inverse f into g, and so on. So it will get P inverse q into x. So this implies that P is nothing but qx into qz inverse. So you can see if I take it on this side, P will be equal to P into qz will be equal to qx, and then P will be qx into qz inverse. So from P equals qx into qz inverse, we can conclude that if qx and P is a full rank, which means rank n, then qz is also full rank, right? So we remember we started with P of full rank. If qx is also of rank n, or then qz will also be a full rank n. So the controllability property of a system is not changed by this transformation, similarity transformation, which is x equals P into z. So the transformation P exists only if qx and qz are a full rank. So P is qx into qz inverse. So if there is an inverse of qz or there is an inverse of qx, only then P will exist. So hence we can conclude that P can take f in and g to controller canonical form fc and gc if and only if qx is a full rank. Okay, so I hope this is clear that we are going to transform from x to z using a matrix P, and then I showed you that the controllability property does not change. So in terms of qz, okay, we can check that the transformation P exists if qx and qz are a full rank, and hence P can take f and g to the controller canonical form only if, or if and only if qx is a full rank. And what is qx? It is the controllability matrix with f and g. So let us continue with pole placement. So let's say that the desired closed loop polynomial satisfy a polynomial which is s to the power n plus alpha 1 s to the power n minus 1 all the way to alpha n, and we are going to denote this polynomial as alpha cs. Okay, so this is the closed loop desired polynomial. In controller canonical form, using fc and gc with gains kc1, kc2 all the way till kcn, the determinant of si minus fc minus gck can be written as s to the power n into a1 plus kc1 s to the power n minus 1, and so on. This we have seen earlier. At least for the cubic example, I worked out all the steps. Here we are doing it, we are extending it to n dimensions, or sorry, in when x is n by 1. So the above gives that ai plus kci is alpha I. So you can easily find the gains if it is given in the controller canonical form. How do we find the controller gains when it is given in the f and g, not in the canonical form? So let's call those k1, k2 all the way till kn. And so these are for the original f and g matrix. This is a very well-known formula in linear controls. This is called Ackermann's formula. I am not going to go into the proof of this formula, and you can please see in many textbooks, for example in Franklin Powell and Abbas Imam Inaini, okay, feedback control of dynamical systems. You can find K, the gains, from this expression, which is 0 0 all the way till n. So this is like a column vector with the last element as 1 into qx inverse and then alpha cf. Okay, what is alpha cf? Alpha cf is nothing but this closed loop polynomial alpha c, where s is now replaced by f. Okay, so there is this very famous theorem called Cayley-Hamilton theorem, which says that the polynomial this should also be satisfied if you substitute f instead of s. Okay, so all we need to do is s to the power n, we'll write f to the power n. S to the power n minus 1 is f to the power n minus 1. Okay, so we can obtain this alpha c with s substituted by f. Then we find the inverse of this controllability matrix, and then we multiply or take the nth component of this, and then we get k. Okay, so this is a very well-known formula which is available in many textbooks, and I don't want to go into details. So for n small, the controller gains can be obtained by solution of linear equations or by inspection. If you have a large n, then we can go back and use this Ackermann's formula to obtain the controller gains. So the natural question is, how do we choose the closed loop poles, or how do we obtain the desired polynomial alpha c of s? So if you have a desired polynomial, then I showed you how we can find alpha c of f, then we know qx inverse, and then we take this component, and then we can find k matrix. But what is this? The natural question is, what is the desired closed loop polynomial, and how do we obtain, or how do we choose this desired closed loop polynomial? So the main idea is to keep u of t small. Okay, what is u of t? U is, remember, minus k into x. So we want to keep the controller input, or the input to the plant, small. Why? Because then we can use smaller actuators. U has to be supplied by some actuator. So in the case of the single link being rotated by a DC motor, U was actually the voltage which we are applying and sending to the DC motor. So we would like to make sure, or try to make sure, that the voltage which you are applying is small. So hence we can use a smaller motor. There are many approaches to choosing this desired closed loop polynomial. Okay, the two most common ones are, we can decide on what is called as a dominant second order system. So we choose two poles near to the imaginary axis in the S plane, okay, such that the response is close to a desired second order system. So if you have two poles close to the imaginary axis, we can easily see what is the settling time, what is the peak overshoot, what is the natural frequency, what is the damping. All those things are clearly defined for a second order system. But if you have a nth order system, we pick two poles, or we say that my system should behave like these two dominant poles. There is also another way, which is called optimal linear quadratic regulator, or LQR design. So we obtain the gains k such that an objective function of y of t and u of t is minimized. So we can create one objective function, then we can minimize that objective function of y and u, and then we can obtain k. So I am not going to go into the details of this optimal LQR design. If anybody is interested, they can look at some advanced control system design book. Let's now continue, and we come to this very important topic called estimator design. So till now we assume that all the state variables are available for control. So this is also called full state feedback. So basically we have u is equal to minus kx. So we could measure all the state variables. There are n of them, and we could find k1 through kn to do some desired closed loop polynomial. Often all states are not measured. So basically it is too expensive or sometimes not even possible. So if you have a complicated plant, so some of the states are not so easy to measure. So instead of u equals minus kx, we would like to use u equals minus kx hat. Okay, so x hat is an estimate of x. So we will measure only some of the x's, and then we would like to obtain an estimate of all the x. Okay, so this is called an estimator, and how do we design a system which can estimate all the state variables from few measurements. So one natural way is to obtain x hat from the model of a system. Okay, so what do we mean by model of a system? The simplest possible model is x hat can be obtained by this differential equation, which is x hat dot is equal to f x hat plus gu. So what is this assuming? That we know the plant f, g and u exactly. So basically then all what is unknown, the initial conditions of x of 0 is not known. So if the initial conditions were known exactly, then the state equations x dot equals fx plus gu can be integrated, and then all the x's can be obtained. But in this estimator design, in this part of the estimator design, or a very simple estimator design which we are discussing, we do not know the initial conditions. We know everything else. We know what is exactly f, g and u of t. So the goal is to design an estimator where the error, which is x minus x hat, is reduced much faster than the natural dynamics. So we will define a new variable which is x tilde, which is x minus x hat. We will design a system such that this x tilde goes to 0 very quickly, which means basically x will become x hat or x hat will become x. So we know x hat, x. So if f and g are not known exactly or not known accurately, x hat will deviate from x even if the initial conditions are not known exactly, because if this differential equation, if this f is different than the plant f, or this g is different than the plant g, then of course x hat will deviate from x. This is a topic in advanced control such as adaptive control, and we will not discuss this in this lecture. So how does the estimator looks like? So basically what we have is u of t coming into the plant. The output of the plant is x of t. Then we have this transfer function or h matrix. So then h into x will give me y, and we are going to measure y. So the same u can be sent to a model which is f and g, and we get an output which is x hat, and then x hat into h is y hat, and we can find the difference between y and y hat, and then this error is sent back into the model. So and through this block which is containing L. So this L is called the estimator gains. Okay, so the equation from this figure is x hat dot is f into x hat plus g into u plus L into y minus hx hat. So y minus hx hat, so h into x hat is actually y hat. So y minus y hat is this quantity here. You multiply that by L, and then you feed it back to this plant or to this model. And what is the basic idea? We are going to choose L to ensure that the difference between x and x hat goes to 0 in a desired manner. So this x tilde goes to 0 in quickly, so that we have x if we know x hat quick. Okay, so if you look at these two expressions, x dot is equal to fx plus gu and x hat dot is this, then if you subtract the state equations from here, what you will get is x tilde dot is f minus LH into x tilde. Okay, so you can see that if I have subtracted x dot minus x hat dot, so we will get x tilde. So the left hand side is x tilde dot, and then we have fx minus fx hat. So this will be f into x tilde and so on. Okay, so this is the error equation or error in the estimate. So what is the characteristic equation for the error x tilde? That is standard. By now we are very familiar. It is determinant of Si minus f minus LH is equal to 0. Okay, so the characteristic equation for x tilde is given by this determinant. So we can choose L such that f minus LH is stable. So basically x tilde does not go off to infinity. So if x tilde goes to 0, x hat will go to x, and this is irrespective of the initial error x tilde. Okay, so the error dynamics needs to go to 0 faster than the dynamics of f, and since f, g and h are identical to the actual plant, the error will be only dependent on the disturbance. So if f, g and h are not known, the error x tilde will not go to 0, but however we can choose L such that the error x tilde is small and stable. So this is the best that we can do with this kind of estimator. And how do we choose or design L? In exactly the same manner as we did for the controller gains K. So we choose the desired estimator characteristic equations, and the poles need to be faster than the controller poles because the controller requires x, so u equals minus kx, and we need to ensure that x hat becomes x before it can be used by the controller. And again, just like the way we chose the controller gains, we'll compare the desired estimator characteristic equation with determinant of Si minus f minus LH is equal to 0, and then we can obtain L by inspection or solution of linear equations. So exactly the same way as we did for controller gains, we can compare term by term and find out L1, L2, L3 all the way till Ln. And is this possible? Can we do this always? Again, the interesting answer is this is possible only if the system is observable. And again, recall what is the observability matrix. We have Q0, which is H transpose, the next term is F transpose, H transpose, and all the way to F transpose to the power n minus 1 H transpose. So the rank of this observability matrix must be n, and only then we can obtain this L, or we can easily see that we can obtain L1, L2 all the way till Ln. So just let us look at the estimator design example. So let us go back and consider the third order system that we had, which is d3y by dtq plus a1 y double dot plus a2 y dot plus a3y is equal to b1 u double dot plus b2 u dot plus b3 u, and we had obtained this transfer function ys by us is b1s square plus b2s plus b3, and denominator is s cube plus a1s square plus a2s plus a3. So in the controller canonical form, if you go back and see your notes or previous slides, the block diagram look like this. So we have an integrator, another one, and then we have B1, then this is B2, and then this is B3, and then there are these feedback of minus A1, minus A2, minus A3. We can also drive or derive another block diagram which looks like this. So basically you have U and then B3 into U, so B3 into U, then we have U into B2 and U into B1, but then you have to do all these integrations and then you have to add A3 coming from here, A2 coming from here, and then this is Y. So this block diagram is what is called as an observer canonical form. This block diagram is what is called as a controller canonical form. Okay, so we can derive both these block diagrams again with suitable transformations. In one case we did that some QX and so on. Here we will do with the observability matrix. Let's not go into that detail, but at least for this example we can get one block diagram which looks like this, and the previous controller canonical form block diagram looked like this. So there is some difference. So the state space representation using the observer, the new block diagram can be written in this form. This X dot, and I am putting a O for the observer canonical form, is FO into XO plus GO into U plus Y is equal to H subscript O into XO. Okay, so X and XO are different. In the controller canonical form, the F matrix was minus A1, minus A2, minus A3, 1, 0, 0, 0, 1, 0, and G was 1, 0, 0. H was B1, B2, B3, and J was 0. J is 0 in both these examples. But in the observer canonical form, the F matrix is minus A1, minus A2, minus A3. So here it was the first row, here it is the first column. The second column is 1, 0, 0, this is 0, 1, 0. Here the rows are like 1, 0, 0, 0, 1, 0. The G matrix in the observer canonical form is B1, B2, B3. And the H matrix is 1, 0, 0. So one interesting thing that you can observe is the H matrix in the controller canonical form was B1, B2, B3 row matrix. Here the G matrix is a column matrix B1, B2, B3. The G matrix in the controller canonical form was 1, 0, 0. Here the H matrix in the observer canonical form is 1, 0, 0. So if you go back and see some books in control theory, or these observer and canonical form and the controller canonical form are in some sense related to each other. Okay, so in some books you will see that they are called dual. Again, I don't want to go into some more advanced control theory terms, but let's continue. So the characteristic polynomial from the observer canonical form can be written as S cube plus A1 plus L1 S square plus A2 L2 S plus A3 plus L3 equal to 0. So L1, L2, L3 can be obtained by comparing term by term with a desired polynomial, because the desired polynomial will be S cube into some alpha 1 S square or beta 1 S square plus beta 2 S and beta 3 equal to 0. And we can compare and see that L1 will be some beta 1 minus A1 and so on. So from the desired estimator poles, we can find out what are these L1, L2, L3. And again, I have mentioned this, I have not proved this. If you can see some advanced control theory book. So this is always possible if the system is observable, or the rank of this QO observability matrix is N. And because it is so easy to obtain the L1, L2, L3 or the estimator gains, F0, G0, HO, these are called the observer canonical form. So after all this theory and general expressions, just let's look at a simple example. So we have this inverted pendulum. So the linearized equation of an inverted pendulum can be written in this form. So x1 dot, x2 dot. So x1 is theta, x2 is theta dot. Okay, so x1 dot is x2, and then x2 dot is omega square x1 plus u of t. So u of t is like this torque, and this omega 0 is g by L. So what you can see is that this is an unstable system. Why? Because the eigenvalues of this are plus minus omega 0. Okay, so it is on the real axis. There is one which is on the left half plane and one which is on the right half plane. Let us continue. We will only measure x1. So remember, for full state feedback we have u equals minus kx, but here we are only going to measure x1. We are not going to measure x2. So, and the available feedback is y is equal to 1, 0 into x. So x is x1, x2. So y is only x1. Let us assume that the two estimator poles are at minus 10 omega naught. Okay, so it is 10 times to the left of the natural dynamics, which is omega plus minus omega naught. The characteristic polynomial in that case is s square plus 20 omega s plus 100 omega naught square. So why did we choose 10 omega naught? Remember, I had hinted, or I had said that the estimator should work faster than the controller. So the x hat should approach x quickly so that it can be used in the controller, which is u equals minus k x hat. So the characteristic polynomial is si minus f minus lh, so determinant of that. So that is given by s square plus L1s plus L2 minus omega naught square. So again, f is this 0, 1 omega naught square 0. Okay, L is L1, L2, H is 1, 0. So if you just substitute and expand all this, this is what you will get. And then you can compare this polynomial with this polynomial, and you can easily see L1 is 20 omega naught and L2 is 101 omega naught square. So just by simple inspection, this is a very simple system, second order system, we can obtain the gains, estimator gains L1 and L2 such that the two estimator poles are at minus 10 omega naught, quite a lot from the original poles which are plus minus omega naught. So we can program this in MATLAB, and then we can give some initial conditions, and initial condition for x is some, let's say 0.10. So the pendulum is tilted a little bit from the 0 position, theta is 0.1, and we do not know what is x hat. So let's assume that the initial conditions for x hat is 0, 0. We can start from 0, 0 always. So if you solve those equations, if you solve the state equations and the estimator equations, then you can see that the plot of x1 and x1 hat, so dark and this dotted line, so initially they'll be different, but very soon x1 and x1 hat will approach. So in less than 1 second they are becoming same. Similarly, x2 and x2 hat, initially they are different, the initial conditions are different, but very soon they will approach each other and they will be exactly equal to each other. Okay, so some small difference might be there in many places of decimal, but x1 is very close to x1 hat, x2 is very close to x2 hat. So we can now also find what is the u. Okay, so u is normally minus k into x. So the dark line shows u. So this is the input which is required to the plant. Now, if you were to use u equals minus kx hat, then what you can see is the u required is more than if there is a full state feedback. So what have we done? We have an estimator which is using only some measurements. Okay, so that is clearly good. I don't need sensors for both x1 and x2. I can only measure x1. But at what cost? The cost is that the U which you require, or the control input that you require, is larger. Okay, so in an estimator, initially the control input will be more, but again, as you can see, after some time, because x and x hat are close to each other, this will also become same. So in estimator design, we assume that F, G, and H are exactly the same as in the plant. So F, G, and H form the model, and they are exactly the same as it is in the plant. The estimator can be implemented in a computer. It need not be a physical device. The controller gain K cannot be as large as one wants. Why? Because the control input is U is minus Kx, is physical. So it is like basically a torque supplied by a motor or some voltage or some current. And we would like to keep U small and as small as possible. However, since the estimator need not be a physical device, why should there be any limit on the estimator gains L? So we can choose the estimator gains very large. So then X hat will approach X much faster, which is good. However, there is a drawback. And it turns out that if you have very large L, it also results in the amplification of the measurement noise, and it affects the actuator. So this is a topic in advanced control, which I don't want to go into in this lecture. But if anyone is interested, they can look at what is the drawback in choosing a large L. So let us continue. We have this state space design. Let's take another example in which the transfer function of the plant is 6 divided by s plus 1 into s plus 2 into s plus 3. We want the desired poles at s equals minus 1.5 plus minus j2. So this is a dominant second order system that we want the controller to follow. The third pole can be arbitrary, and let's choose it far to the left. So we have s minus 10. So the basic idea is that the effect of the third pole will die out very quickly, and the controller and the system will behave with this dominant second order system. In the form of ODE, the differential equation is d3y by dt cube plus 6y double dot plus 11y dot plus 6y is equal to 6u. In state equations, we can rewrite this as x dot as 0, 1, 0, 0, 0, 1, minus 6, minus 11, minus 6, x into 0, 0, 6. This we have seen earlier. And the output equation is, we will assume that we are only going to measure one of the states, so x1. So let's consider the control input, which is u is minus kx, where k is k1, k2, k3. The characteristic polynomial with the control input is determinant of si minus f minus gk, and we will get a cubic polynomial which is s cube plus s square into 6k3 plus 6 plus s into 6k2 plus 11 plus 6 plus 6k1. Let's look at the desired characteristic polynomial. Remember, we have chosen two dominant second order poles at minus 1.5 plus minus 2j. So this will be s plus 1.5 square plus 4 into s plus 10. The third pole is at minus 10. So if you expand this, you will get s cube plus 13s square plus 36.25s plus 62.5. So now again we can compare term by term. So basically 6k3 plus 6 is 13. 6k2 plus 11 is 36.25. 6 plus 6k1 is 62.5. and then we can solve these equations, very simple 3 linear equations, and then we'll get K1 as 9.4167, K2 is very close to 4.2083, and K3 is 1.1667. We choose the estimator poles faster than the controller poles. The controller poles were minus 1.5 plus minus 2j and s equals minus 10. So let us choose the estimator poles as minus 7.5 plus minus 10j and S3 as minus 50. So roughly 5 times faster than the controller poles. So we can now obtain what is L1, L2, L3 by looking at the characteristic polynomial for the estimator, which is determinant of Si minus F minus LH, which is S cube plus S square into L1 plus 6 plus S into 6, L1 plus L2 plus 11 plus 11 into L1 plus 6L2 plus L3 plus 6. So again, by comparing term by term, basically we can again solve for L1, L2, L3. Why? Because what is the characteristic polynomial of the estimator? That we know. We have chosen the two poles at minus 7.5 plus minus 10j and S3 as minus 50. So then the characteristic polynomial is S cube plus 65s square plus 906.25s plus 7812.5. So we can compare these two cubics, and then we see that L1 is 59, L2 is 541.25, and L3 is 3910. So we can easily solve for the estimator gains L1, L2, L3. And we can again plot the states. This example, we can choose x0 as 0.1, 0.2, 0.3, and the x hat initial conditions are 0, 0, 0. And again, we can solve these two differential equations. One is x dot is f minus gk plus gk into x tilde, and x tilde is f minus lhx tilde. So we can solve these two differential equations. So there are six differential equations. Remember, x is 3 by 1. X tilde will also be 3 by 1. We can solve all of them with these initial conditions, and then we can plot x1 and x1 hat, x2 and x2 hat, and x3 and x3 hat. So what you can see is, after a very short time, less than 0.5 seconds or about that time, x1 and x1 hat are very close to each other. x2 approaches x2 hat, or x2 hat approaches x2, and x3 hat approaches x3. So even though the initial conditions are very different, the estimates match the states. We can also plot u and u hat. Remember, u is minus kx and u hat is minus k into x hat. And again, you can see that initially u hat is more. So although we are only measuring few things, so we are gaining something, but at the cost of more actuator input, at least initially. The same story as what happened for the inverted pendulum. So continuing with the state space design, let us look at the block diagram. So we have a plant which is given by x dot equals fx plus gu. There is an input u of t, the output is x of t, there is a sensor. So we get y is equal to h into x. Okay, then this y is fed back into this estimator, because we are only using some measurements y, and then we also have u coming into this estimator, and the output of the estimator is x hat, and then we have minus k into x hat is the controller, and that is what is u. So this kind of block diagram explains where is the plant, where is the sensor, where is the estimator, and where is the controller. So this can be represented mathematically using these symbols. So first let us define x tilde, which is x minus x hat. The controller is u is equal to minus k x hat. So remember, x hat into minus k. And then we have x dot is equal to fx minus gk. Now instead of writing x hat, we can write x minus x tilde. The estimator is x tilde dot is f minus lh into x tilde that we have seen. So the overall system dynamics is given by x dot is equal to f minus gk into x, and then the gk into x tilde. Okay, and x tilde dot is f minus lh into x tilde. So the characteristic polynomial of this overall system containing the controller as well as the estimator can be obtained by the determinant of this matrix, and that is determinant of Si minus f minus gk, and you can show that the second term is again a determinant which is Si minus f minus lh. So the determinant of this whole system is a product of two determinants, and this is very important and very useful. What it is telling you is that the product of two determinants are 0, and hence we can design the controller using first this part, and then we can design the estimator using this part. So the controller and estimator can be designed separately. This is a very, very nice feature of the state space design. Till now, we have not considered the reference input. Till now, R of t was 0. This in control theory is called as a regulator problem. So we have designed a regulator with R of t equal to 0. So for a single input, single output plant and output, we have x dot is fx plus gu. We have seen this many times now, and y is hx. To include a reference input or R of t, we need to modify the controller and the estimator. So one way is to rewrite the estimator equation as x hat dot is f minus gk minus lh into x hat, and then we add this ly and mr. Okay, so previously up till here it was the estimator equation, but now we are adding this mr. We can also modify u, which was minus k into x hat plus something into nr. So this m and n matrices, or this matrix m and n, does not affect the characteristic equation or poles of the controller estimator. So the stability is in no way affected when we choose some m into r and n into r. So the m and n affects the zeros of the transfer function between y and r. Okay, so they change the transient response. So the question is, how can we choose this m and n? So there are many ways of choosing m and n. Okay, so let's go back and rewrite this x hat equation. Look at it again. X hat dot is f minus gk minus lh into x hat plus ly plus mr, and u is minus kx hat plus nr. So the transfer function between r and s, okay, r and u with y of s equal to 0 will have a 0 if determinant of this is equal to 0. Okay, so transfer function of r divided by u of s will have a 0 in the numerator, because we want to change the zeros to obtain a good or a desired transient response. So the 0 will occur if the determinant of this complicated thing is equal to 0. So what is this? The first term is Si minus f plus gk plus lh, and this is minus m, and this is minus k, and this n equal to 0. So the characteristic equation for this determinant is, again, we can find a polynomial gamma of s, which is determinant of Si minus f plus gk plus l into h minus 1 by n into m into k equal to 0. So we can choose this m and n to get the desired zeros in the transfer function between rs and us. One thing to be kept in mind is that we do not want any pole zero cancellation. So we do not want a zero which is sitting on top of a existing pole. So let's look at an example. So we have a plant transfer function which we have looked at before, which is 6 divided by s plus 1 into s plus 2 into s plus 3. We want the dominant second order system with desired poles at s equals minus 1.5 plus minus 2j. The third pole, as we had discussed earlier, could be far to the left, sort of arbitrary. Let's choose it at s equals minus 10. So we have u equals minus kx. We have done this earlier and we showed that k1 is 9.41 so on, k2 is 4.208 and so on, and k3 is 1.1667. We can give this system in MATLAB and we can plot the step response for such a system with full state feedback, and it looks like this. So we have this step response, and this is the amplitude, and you can see that the rise time is 1.22 and so on. The settling time for 5% is 2.19. The peak time and the peak overshoot are given by 1.69 approximately, and MP is 0.09. Okay. So, but we had also designed the same system. We had looked at the same system and designed a controller based on compensators. Okay, remember, if you go back and see the results long time back, we had taken the same system and we had designed a compensator for that to meet certain requirements, to again meet the same dominant closed loop requirements. So in that case, again, we had the same system, the same desired poles, the same third pole at s equals minus 10, and we did a controller design using root locus and a compensator. So please go back and see that the compensator which we designed was 31.4 into s plus 4 divided by s plus 15 and s plus 5 divided by s plus 18.15. So these were designed such that the angle and the angle at that desired poles, the angle was minus 180 degrees. And again, we can find the step response of this system with this compensator, and the step response looks like this. So from the step response, and again using MATLAB, okay, toolboxes, we can find what is the rise time, what is the settling time, what is the peak time, and what is the peak overshoot. Using state space design, we can also obtain what is the rise time, settling time, time for the peak overshoot, and so on. So the difference between these two designs are several. One is, in this design, the system settles at around 0.7, whereas here the system settles at around 0.1. So there is a steady state error for this design, whereas there is no steady state error for this design. The other parameters like rise time and settling time and TP and MP peak overshoot are sort of similar. Okay, but you can see that the design using state space looks like better. Okay, and in fact it is also easier. So there are lots of software tools which can be used to obtain this state space design, whereas when you want to do compensator design, it is a little bit more complex and you have to do some trial and error. There are many more steps, whereas the state space design is becoming very, very popular, and we can have control toolbox in MATLAB and various other software tools which can very quickly tell you what should be the controller gains and even estimator gains and so on. So in this example, we have used full state feedback, but we could have also continued and seen what is the effect when you have an estimator. So that is not done in this example, but it can be done. So in summary, a controller based on availability of all state variables is very easy. So we can easily find u equals minus kx, and we can design the k or choose the k such that it meets the desired closed loop polynomial, okay, just by comparison. We can achieve arbitrary pole placement to obtain desired specifications. So remember, the desired closed loop polynomials could be anything, and we can still find k's, okay, such that the desired polynomial or the performance which is captured in the desired polynomial is achieved. And when is this possible? It is always possible if the system is controllable. So the controllability matrix must be a full rank. We can also use observers to estimate the states if you have limited number of measurements. So we do not want to measure all the states, especially if the system is large, when the number of state variables are large. So in that case, we use an observer. We can use these observers to estimate the states, and we can design these estimators such that it very quickly follows x hat will follow x. Okay. And when is this possible? It is possible if the system is observable. We can also introduce reference input, and this has to do with the zeros of the system. So basically, when you introduce a reference input, the transient response changes. The poles of the transfer function or the poles of this system remain more or less the same. So it does not affect the stability of the system, but the reference input will change the nature of the transient response. Another very big advantage of state space design is that it can be used for MIMO system. So although it has not been discussed in this course or in this lecture, we can easily find in many textbooks where the state space design is being used for multi-input, multi-output systems. So with that, we come to an end of this week. So in this week, we have looked at 3 different ways of designing controllers: PID controllers, root locus based controllers, and also state space based designs.